G'day all, welcome to another CUDA tute. So, in CUDA we usually launch many threads in groups of thread blocks that form a grid. That's good. Let's say we've got two arrays right here, array 1 and array 2, and we want to add the values in array 2 to their corresponding values in array 1. Perfectly normal thing to do, quite common, but this is how you might tackle it in C++. You'd use a for loop, possibly. So for int a equals 0 while a is less than 6, a plus plus, then you just add them, the elements one after another, and it might look something like this. So the for loop would iterate 6 times, adding an element each time. That's the way that C++ works. In CUDA, on the other hand, what we sort of do is we make 6 threads, and each thread takes care of a single addition, and they're all performed at the same time. So instead of a loop of 6 iterations, we make 6 threads. Let's have a look. Bang, something like that. So maybe the first thread, thread 0, would take care of the first addition, and the next thread would take care of the second addition, etc., etc., etc. But they would all run at the same time. Sort of. Yeah, so this is kind of the hello world of CUDA. This is just kind of the most basic use of the GPU. And we'll code this at the end in an example. It's pretty cool, actually. Okay, but before we get to coding, we've got to go through 100 million terms. So let's just get stuck into it, shall we? Threads. Threads are a single execution unit that runs a kernel on the GPU. So they're similar in many ways to CPU threads, but there's usually more of them. And they're sometimes drawn in the NVIDIA documentation, for example, as an arrow with a squiggly line, just like that. Little thread. Okay, thread blocks are a collection of threads. So all of the threads in a single thread block can communicate. Yeah, it's just a whole bunch of threads all together and they can communicate. So here I've drawn out a little thread block. It's just a square with 8 threads inside it. And all of the threads in the same thread block can easily communicate. And the grid, when we launch a kernel, we launch a collection of thread blocks. And each thread block has a bunch of threads in it, like we just said. So the grid itself is a collection of thread blocks, and thread blocks are a collection of grids. Thread blocks are a collection of threads. Oh, I'm going to lose it here. Okay. The grid might be drawn something like this. So here I've got, 4 little thread blocks, and each thread block has 8 threads in it. Okay, that's cool. dim3. Yeah, it's another term. So the dim3 structure is really, really important in CUDA. It's just a little structure with x, y, and z as integers. And yeah, you can initialize them like this if you want. So dim3 threads 256. That's going to make a new dim3 instance called threads with x set to 256. Y and z, the other 2 dimensions of our 3-dimensional dim3 structure, will actually be set to 1. And the reason for that is that you multiply the dimensions quite a bit, and if they were initialized to 0, anything multiplied by 0 just gives you 0, so that would be no help at all. So they're initialized to 1. Or we can initialize both x and y with something like this: dim3 blocks 100 100 in brackets as my parameters, and that's actually going to initialize x and y to 100, but z's still going to be 1. So here my dim3 structure instance will be called blocks. Finally, if you want to initialize all 3 dimensions of your dim3 structure instance, you can put 3 values in the brackets, so 10, 54, 32. This is going to make a dim3 structure instance with x set to 10, y set to 54, and z set to 32. Yeah, we'll see dim3s a lot more. Anyway, kernel invocation. The host calls a kernel using the triple chevron notation. Yeah, chevrons are just the less than and greater than symbols, so less than, and then, something there, the launch configuration, then greater than, greater than, greater than. Inside the chevrons we place the number of blocks and the number of threads per block that we want to run the kernel. Yeah, so the following launch or the following would launch 100 blocks of 256 threads each for a total of 25,600 threads. Yeah, these numbers just here, the number of blocks and the number of threads per block is called the launch configuration. So something like this, some kernel, that's the name of my kernel that I'm calling, and then open up the triple chevrons, and then 100. That 100 just there is the number of blocks to launch, and the 256 is the number of threads per block. And then you close your triple chevrons and you put your parameters in brackets. I've just put ... there, but that would be your parameters. This one, on the other hand, would launch 50 blocks of 1024 threads each, for a total of 51,200 threads. Yeah, so you just put the blocks first, the number of blocks first, and then the threads per block. And collectively there you've specified the size of the grid, really. 50 blocks, 50 blocks and 1024 threads per block. That's my grid. You can also launch kernels with 3D grids and blocks. Yeah, using DIM3, we'll look at that later. Yeah, you can really start to see the difference between the GPU and the CPU. I'm not sure what would happen if you tried to launch 51,200 threads on a CPU, but it wouldn't be good. Yeah, it'd be pretty funny. I don't know what would happen. It wouldn't be funny haha either. It'd be funny crash. Yeah, some maximums. You can launch up to 1024 threads per block. Yep, that's just a maximum. You can't put 1025 threads in a block, your kernel won't launch. If you've got an older card with compute capability 1.3 or less, then your maximum is actually 512 threads per block. Yeah, we'll look at compute capability later on. That's the physical capabilities of your GPU. You can launch 2 to the power of 32 minus 1 blocks in a single launch, or 2 to the power of 16 minus 1 if your card is compute capability 2 or less. Yeah, so you can launch a massive number of blocks, but each block can only hold sort of, a certain number of threads. The number of threads per block is quite small, but the number of blocks you can launch is quite big. So my relatively inexpensive GeForce GT 440, which I've got running in this beautiful computer, can launch a rather ridiculous 67 million threads without a hiccup. Yeah, it sure can. Absolutely crazy. Okay, so why blocks and threads? Yeah, you might be wondering why not just say launch 67 million threads instead of organizing them into blocks as well. Why the additional abstraction? Each GPU has a limit on the number of threads per block, but almost no limit on the number of blocks. And each GPU can run some number of blocks concurrently, executing some number of threads simultaneously. Yeah, basically what ends up happening is that you tell the kernel to launch, say, 100 blocks of X number of threads, and a really high performance GPU might run, say, 10 of those blocks at once, whereas a really low end GPU might run 2 of those blocks at once. But eventually, both GPUs will chew through the workload and get to the end. But in making the additional abstraction of blocks of threads, NVIDIA's really just made a really simple way that a high-power GPU can run exactly the same code with no changes whatsoever and get better performance. Clever stuff, really. Alrighty, so each thread is an individual. Each of the running threads is an individual, and they know the following. Thread index or thread IDX. These are all DIM3 types, and we use these inside the kernel. We'll see in just a minute, and at the end in the example. Thread index is the thread index within the block. Block index or block IDX is the block index within the grid. Block dim is the block's dimensions in threads, and grid dim is the grid's dimensions in blocks. Did I say that right? That's so confusing. Block... I'm not going to try again. Anyway, each of these are DIM3 structures, and we can read them in a kernel to assign particular workloads to any thread. Yeah, and this is what we're going to do at the end, so we better have a bit of a look at it. This is a really common pattern. It's common to have threads calculate a unique ID within the kernel to process some specific data. If we launch a kernel with this, some kernel is the name of my kernel, then we've got our open triple chevrons, and then for my launch configuration I say 100 blocks and 25 threads per block, and then I close my triple chevrons and I put in the launch parameters. Inside the actual kernel itself, each thread can calculate a unique ID with something like int ID equals, and then block ID x.x multiplied by block dimensions.x plus thread index.x. And with this line just here, if every one of those, what have we got there, 2500 threads, if every one of those 2500 threads calculates this little line out here, it's always going to come up with a different unique value. So the 5th thread of the 4th block would calculate its ID to be 100, whereas the 14th thread of the 76th block would calculate its unique ID to be 1914. And in that way, what we end up doing is, having a unique number. So maybe this thread just here, the 5th thread of the 4th block, could work on an array element number 100. And at exactly the same time, this one down here, the 14th thread of the 76th block, could be working on array element 1914 or 1914. We're about to do exactly this in an example, but I do just want to pause it because I don't think I'll get through it in one take. Alright, see you on the other side. Alrighty, g'day all, I'm back again. We're just going to make a little CUDA kernel that adds the values from one array to those in another. Okay, let's go. Include IO stream. Why not? Include CUDA.h. I'm also going to go include stdlib.h. I think that's got rand in it. And ctime, so that we can randomize the timer. Those are just C++ includes. Alrighty, so I'm just going to set up 2 arrays in C++. So I'm going to call them h_a equals new int, and we'll say count. I'm going to go up here, int count equals 100. Okay, 2 little arrays in C++, and then I might just initialize them to random values. So int I equals 0, or I is less than count, I plus. And we want, what's that, h_a equals rand, mod maybe 1000. h_b equals much the same thing. And then we might print out just the first, say, 5 values for int I equals 0, or I is less than 5, I plus, and cout h_a. What am I doing? And h_b, a handle. Prior to addition, alrighty, so I've just made two little arrays. They've got 100 integers in them each. They're all on the host. That's why I put h_ and then the name of the array, which is A or B, and each of those 100 elements is set to some random integer from 0 to 1000, and I'm printing out the first 5 of those. Let me just run this and make sure we've got no errors. Oh yes, we've got errors. Int has been admitted. Yeah, it has too. Well spied, C++. He's good, this compiler. What do we got now? Oh yeah. Okay, it helps. It helps if you put an element index to your arrays when you're trying to set them to random values. Oh, where's it gone? Let me put a breakpoint there. I think it ran okay though. Yeah, good stuff. So they've just got random values in them. Alrighty, so now the first thing that we've got to do is make some device versions of exactly that. So d_a and d_b. These are going to be the device copies of those arrays. And the first thing that we want to do is allocate memory on the GPU for them. So I'm actually going to check for errors as well, because I want to do this properly. ampersand d underscore a, we got size of int multiplied by count. Yeah, so if that doesn't equal CUDA success, then cout nope and return 0. Alrighty, if we don't allocate the memory for the D array, then we return 0 and just get out of there. You know, the program broke, so just run away. We also better allocate for memory for the device's B array, so I'll just copy that because it's much the same thing. Okay, so if A or B don't allocate properly, then we just say a little message. I should actually say here no, 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 no. Okay. Yeah, if A allocates for some reason and then B doesn't, then we might just want to free A before we return. Anyway, that's not really important. So the next thing that we're going to do is actually copy the values. So we've allocated enough space for, what is it, 100, which is our count. We've allocated 100 integers worth of space for 2 arrays on the GPU, but we haven't copied the values from the host's arrays to the GPU's arrays. So we'll do that next. If, was it CUDA man copy? Always type an O in there. Never mind, don't tell anyone, they won't know. Size of count, that's the number of bytes that we want to copy, and what are we doing here? CUDA mem copy host to device. If that doesn't equal CUDA success, then we say no. And I might free both of those arrays since they were copied, but they couldn't be. I'm sorry, they were created, but the data couldn't be copied. Okay, so that copies the host's A array values over to the device's copy of exactly the same thing. So if that comes out okay, I mean, if that comes back as CUDA success, then yeah, we'd better do the same thing for the B array. Copy that from the host. So I can just copy the same code and change a few things around. The destination and the source have to be the B array this time. And the rest of it should be the same, I think. We should actually go down here and do delete HA as well, instead of being a naughty boy and leaving them. Okay, so at the moment we've copied the 2 arrays, or we've created the 2 arrays on the GPU and the host, and we've also copied exactly the same values. So now we're ready to launch our kernel, which doesn't exist. That's good. I might call it add ints, and my launch configuration might be count divided by 256 plus 1. So that's the number of blocks that I want to launch. It's whatever my count is divided by 256 plus 1, and the 256 comes about because I want to launch 256 threads per block. Does that make sense? So if count is something like it is at the moment, 100, 100 divided by 256 is going to give me 0, since it's integer division, and you know we can't launch 0 blocks, so that's where the plus 1 comes into it. Anyway, I'm basically launching here enough blocks and threads to take care of any array whatsoever. If I change count here up to 42 million, it's just going to do it. Oh, maybe no, 42 million might be too big. If I change that to 1024, it could handle 42 million. D, B, and count. Okay, so that's my launch configuration just there. Yeah, those are the 2 arguments or the 3 arguments I'm passing, and after we've done that, we want also to if CUDA man copy h underscore a d underscore a size of int multiplied by count, and CUDA mem copy. CUDA mem copy what? CUDA mem copy what? CUDA mem copy lowercase c, that's what. Device to host equals CUDA. Oh gosh, I can't type success more than sort of 3 times in a row without putting in some wrong things. Anyway, if it doesn't work out, then just return 0 to free these things. Okay, so once we've launched the kernel, we've got to copy the results that the GPU calculated back to the host's A array. So that's what I'm doing here in this line just here. We're copying from device to host, and if that doesn't work out, if that returns something, whoops, if that doesn't return CUDA success, then we'll just delete the things and maybe say nope again. I don't know, it's up to you. If it does work out though, we want to for int I equals 0 while I is less than, say, 5. We might just print out the first 5, shall we? I plus plus, cout its, and A underscore A 5 ender. Yeah, if that does work out, then we'll just print out the first 5 to make sure that the GPU actually performed the addition properly. And at the very end, we also should free the GPU's arrays. Okay, so that should all be pretty good, assuming that I've got no typos. What we've got to do now is actually create the kernel. So it's global, which means that it's callable from the GPU, but it's going to run on the, sorry, it's callable from the CPU, but it's going to run on the GPU. Add ints, and it takes int star A, and int star B, and int count. Alrighty, so those are the arguments that I passed it in the launch down here. D underscore A, D underscore B, and count. So all that this kernel's actually got to do is add each of the items from B to the items in A, but it's going to do that by calculating first of all a unique thread ID for each of the running threads. Equals, what's that, block ID x dot x. No, it's multiplied by block dim dot x plus thread ID x dot x. Okay, in this way, each of the running threads, and there's going to be hundreds of them running at once, possibly, each of them is going to calculate a unique index, and it can use that index to add its particular elements together. So its particular element from the B array to the value in A. What we've got to do also is say if ID is less than count. So some of the threads that are running might actually calculate an ID that's outside the bounds of these arrays, and we want those particular threads just to come down here and not do anything. We don't want them to read and write outside the bounds of the array on the GPU. That'd be a disaster. Okay, so all we have to do in here is ID plus equals B ID. Okay, so each thread takes care of one particular addition, but many of them run at once. Let's see how we go. See how many typos I've made. Oh, you're joking. It ran the first time. That's unbelievable. Anyway, each of those threads added together one element. So the 0th thread, or the thread that calculated its ID to be ID equals 0, added the 614 to 811 and came out with 1425. And the next little fellow went along and calculated 1114, and so on and so on. And there was actually 100 of them that all ran together. If I just hit stop and we change this to some bigger number, so let's say the count of our array is something slightly larger, maybe 1000, 1000, and hit play. Bingo. Easy as that. So it almost doesn't matter how big the arrays are. These threads will take care of it. No worries. And they'll do it sort of all simultaneously as well. And I hope that was a useful little introduction there. I know it was quite long, but yeah, we really got to get through this sort of basic stuff first before we get onto something really interesting. And this is pretty exciting in itself, really. Pretty good stuff. Anyway, thank you for listening. See ya.